We can evaluate limits with a table of values. The general statement for a limit for some function f of x, where x is approaching a, is seen on the screen. So we see the limit notation, LIM, x is approaching a, for some function named f of x, and we say that that's equal to a limiting value that we call L. Remember, L is not necessarily what the function is equal to when a is plugged into it. L describes the behavior of the function outputs as we're approaching that input a. So for a generic graph, we can talk about a being some value on the horizontal axis, L is some value on the vertical axis, and we want to pick points that are just left of a and just right of a. We'll evaluate our function at those points and then look for a trend in the table of values. On the screen you see a generic table that we can use to evaluate any limit for any function. All we need to know is, what is x approaching? In other words, what is the a for the problem I'm trying to solve? And then you can build the table around it. And then what's the definition of the function that I'm investigating? You can plug all of your x values into that function's definition to complete that right column of the table. The first three rows of this table are the values of x that are approaching a from the left-hand side. So notice that these x values all start with a, and then we're subtracting a very small value from it, which means the x value is something a little bit smaller than a. It's on the left-hand side of a. When we plug those values into our function, we're going to look for a trend. Are the outputs starting to get closer to a particular number that we can identify? The last three rows of the table are the values that are approaching a from the right-hand side. Notice that these x values start with a, and then we're adding a tiny amount to a. So these are all values larger than a. They're on the right-hand side of a. We'll plug those into our function and again look for a trend. Can we identify a single value that this function is tending to? Let's go ahead and give it a try with a function. Let's look at x squared minus 4 divided by x minus 2. We have the function graphed. We can see where x equals 2 is at and that the corresponding point on the function is missing. But if it were there, it would be equal to 4. We need to pick some values of x left of 2, some values of x right of 2, plug them into our function to build our table to determine the limits. Notice that I've replaced all of the a's in the table with 2 because our limit notation tells us that we're approaching x equals 2. Replacing all of the function points with what they're equal to at the corresponding x values, we can complete the table of values, and now we're going to read the table to determine if there's a limiting value that we can identify. Starting with the left-sided limit, as we're approaching 2 from the left, we can see a trend in our outputs. All of those outputs are inching closer and closer to 4. What about from the right-hand side? Looking at the x inputs that are just right of 2, getting closer and closer to 2, can we see a trend in the function outputs? Yeah, they're also getting closer and closer to 4. We've identified the limiting value for this function when x is approaching 2. It is equal to 4. So we can always use a table of values to evaluate our limits. Although it's a little bit tedious, it will usually give us some insight into what's happening with our function. Here's another function, sine x over x. This is a function that we will see again and again in the course because it's a little bit tricky when it comes to algebraically evaluating limits. But for now, let's take a look at this function using our table of values. We need to look at our function and our notation to determine what exactly we are approaching. So we're looking at approaching x equals 0, so our a value is 0. And we want to look for a trend where we can identify the limiting value L, which would be on the y-axis. Now just looking at the graph, we might suspect that it's approaching 1, but we're going to double check using our table and see what we can conclude after we've evaluated the function at various points on the left and right side of 0. Plugging in the values for x left of 0 to our function, we can look for a trend in our function outputs, and it does look like they're heading towards 1. Same thing with the right-hand side. The values of x that are on the right of 0, plugging those into our function, we can see a trend where our function outputs are tending to 1. So the limiting value for this function is in fact 1, just like we suspected when we were looking at the graph of the function. Let's try another one. The limit when x approaches 4 for the function square root x minus 2 divided by x minus 4. The a value from our limit notation is 4. Our input value is approaching 4, so we replace all of the a's with 4, and then we update our table to show what the values of x will look like in our table, and that will allow us to pick some of the points that are left of a and some of the points that are right of a. Looking at the x values that are approaching 4 from the left and the corresponding function outputs, we can see a trend. Notice that each of these outputs starts with 0.25, but it's the digits that follow that are different. For the x value 3.9, that's the farthest point that we're using left of 4, we have the largest value of our function output, and as we get x values closer and closer to 4, our function outputs are shrinking. So the decimal digits that are following the 0.25, they get smaller and smaller. So we can see a trend here that those digits that are following the 0.25, they're going to all turn into zeros as we get closer and closer to 4. So from the left-hand side, it looks like our function behavior is pushing us towards 0.25. Looking at the values from the right-hand side, we see a similar trend, but notice that the point that is the farthest away from 4 on the right-hand side, 4.1, that has the smallest function output, and as we get closer and closer to 4, our function outputs are growing. They look like they're growing towards 0.25. Now maybe you're not completely convinced with this table of values, and that's fine. It's okay to be skeptical. Throw some more points in here. Test 3.9999 and 4.0001. You'll notice that the function outputs are getting even closer to each other and even closer to 0.25. So the limiting value of this function is 0.25, and we can see it from the table.